For billions of years, the stars have been our cosmic architects. They are the roaring furnaces that forged the very elements inside our bodies, the celestial lighthouses that illuminate the vast galaxies, and the gravitational anchors that define the structure of the universe itself. Every sunrise we witness is a testament to this grand cosmic cycle, the relentless fire of nuclear fusion burning silently in the hearts of distant suns. But as with all things, this, too, shall pass. Nothing, not even the stars, lasts forever. Even the most resilient stars, the red dwarfs destined to burn for trillions of years, will one day run out of fuel. Our universe isn't a static masterpiece. It's a dynamic, aging entity, and its magnificent engines are slowly, inevitably, winding down. This journey isn't about the universe we see today, a vibrant cosmos bursting with starlight and blazing galaxies. This is about the universe that is yet to come, a future where the last embers of creation finally fade, where an all-encompassing darkness replaces the brilliance, and where only the faintest, most ghostly whispers of energy remain. Together, we'll journey down the incredibly long timeline of stellar death. We'll start with the dramatic collapse of massive suns into exotic neutron stars and enigmatic black holes, and follow the story all the way to the quiet, dignified extinguishing of the universe's smallest, longest-lasting red dwarfs. And once the very last star flickers out, what happens then? Could new strange forms of stars ignite from the ashes? Will colossal black holes become the silent rulers of an eternal night? And what becomes of life, of energy, of meaning itself, when the entire cosmos finally goes dark? These aren't questions about our immediate future. The events we about to explore will unfold over timescales so mind-bogglingly vast, trillions upon trillions of years, that they make the current age of the universe seem like a mere blink of an eye. Yet, armed with the powerful tools of physics, astronomy, and cosmology, we can peer into this ultimate fate. We can begin to sketch a picture of the end. The story of the last stars doesn't begin at the end, however. It starts at the very beginning, because to truly comprehend how stars die, we must first understand how they live. And that's where our exploration begins. Have you ever looked up at the night sky and wondered if those twinkling stars will shine forever? The truth is, they won't. Stars aren't eternal flames. They're cosmic engines, powered by a delicate dance between gravity and pressure. To understand their story, we need to trace their lives from a fiery birth to a spectacular death. Our journey begins in the coldest, darkest corners of space, inside what we call molecular clouds. These are enormous, chilly expanses filled mostly with hydrogen and helium gas. Think of them as stellar nurseries. Within these clouds, gravity, the universe's ultimate sculptor, starts pulling gas and dust together into dense clumps. As more and more material falls inward, the clump gets hotter and denser, forming a glowing baby star, or what astronomers call a protostar. For a long time, this protostar is just a hot, compressed ball of gas. But as gravity continues to squeeze its core, something incredible happens. The temperature and pressure become so extreme that hydrogen atoms, the most abundant element in the universe, are forced to fuse together, creating helium. This process, nuclear fusion, unleashes a colossal amount of energy. This energy pushes outward, perfectly countering gravity's inward crush. This is the moment a protostar truly becomes a star. It's no longer just a glowing ball. It's a self-sustaining nuclear reactor, held in a perfect state of balance, called hydrostatic equilibrium. This equilibrium is the secret to a star's long and stable life. Once a star ignites, it enters the longest and most stable phase of its existence, the main sequence. Astronomers use a chart called the Hertzsprung-Russell diagram to classify stars based on their brightness and temperature. And most stars, including our Sun, spend about 90% of their lives here. But not all main sequence stars are the same. A star's mass is its destiny. It dictates its color, its lifespan, and how it will ultimately die. Let's look at the different classes. First, we have the heavyweights, the massive, brilliant blue stars. These are the rock stars of the cosmos. They're incredibly hot, incredibly bright, and they live life in the fast lane. They burn through their hydrogen fuel at a furious pace, shining thousands of times brighter than our Sun. But this extravagant lifestyle comes at a cost. Their lives are astonishingly short, lasting only a few million years before they burn out. Then we have the middleweights, stars like our very own sun. These are the steady, reliable citizens of the galaxy. They burn yellow-white and maintain a stable output of energy for billions of years. Our sun has been shining for about 4.6 billion years. It's only about halfway through its main sequence life. These stars provide the long-term stability that can allow complex systems like life on Earth to evolve. Finally, we have the lightweights of the stellar world, the red dwarfs. These are the most common type of star in the universe, but they are so small and faint that you can't see a single one from Earth with the naked eye. They are incredibly frugal, sipping their hydrogen fuel so slowly that their lifespans are almost unimaginably long. We're talking trillions of years, far longer than the current age of the universe. The very first red dwarfs are still in their infancy, with countless ages of shining ahead of them. So, mass is everything. A star's initial mass sets the clock for its entire life. But what happens when the fuel runs out? Every star, no matter its size, eventually exhausts the hydrogen in its core. When this happens, nuclear fusion falters, the outward pressure weakens, and the delicate balance is broken. Gravity, which has been held at bay for millions or billions of years, begins to win the fight. What follows next depends, once again, entirely on the star's mass. For low-mass stars like our sun, the end is a slow, graceful process. When the core's hydrogen is gone, the star's outer layers swell up dramatically, cooling and turning red. It becomes a red giant. Our sun will one day expand so much that it will engulf Mercury, Venus, and possibly even Earth. After this phase, the star sheds its outer layers, creating a beautiful, glowing cloud of gas called a planetary nebula. At the center of this nebula is the star's exposed core, a white dwarf. A white dwarf is an incredible object. It's about the size of the Earth, but contains the mass of the sun, making it extraordinarily dense. It no longer produces new heat. It's just a cooling ember that will slowly fade to black over trillions of years. The death of a massive star, however, is anything but graceful. It's the most violent and spectacular event in the cosmos. When a massive star runs out of fuel, gravity causes its core to collapse in an instant. This catastrophic collapse triggers a mind-bogglingly powerful explosion known as a supernova. For a few weeks, a single supernova can outshine its entire host galaxy. But these explosions are not just destructive. They are the universe's grand creative acts. During a supernova, the extreme temperatures and pressures forge elements heavier than iron like gold, silver, and uranium. The explosion then blasts these new elements across space, seeding the surrounding gas clouds with the raw materials needed for new stars, new planets, and even life itself. Every atom of carbon in your body, every bit of oxygen you breathe, was forged in the heart of a dying star and scattered by a supernova. We are, quite literally, made of stardust. After the fireworks of the supernova fade, an exotic remnant is left behind. For most massive stars, it's a neutron star. This is a city-sized sphere, so dense that a single teaspoon of its material would weigh billions of tons. But for the most massive stars of all, gravity's victory is absolute. The core collapses completely, crushing matter out of existence and forming a black hole point of infinite density, where gravity is so intense that nothing, not even light, can escape. This incredible cycle of stellar birth, life, and death has been repeating across the cosmos for billions of years. Gas clouds collapse to form stars. Stars live and die, some gently, some violently. There. Death throes enrich the universe with heavy elements, which are then swept up into new clouds, forming the next generation of stars and planets. It's the ultimate cosmic recycling program. But here's the crucial point. This recycling isn't perfect. It can't go on forever. With each generation of stars, more and more matter gets locked away into stellar remnants. White dwarfs, neutron stars, and black holes are cosmic cul-de-sacs. They hold on to their mass and don't return it to the interstellar medium to form new stars. So, while the universe is still young and brimming with star-forming gas, the total supply is finite. Over unimaginably long timescales, trillions of years, the available gas will be used up. The rate of star formation across the cosmos, which has already passed its peak, will continue to decline. The stellar nurseries will grow quiet and cold. Eventually, the last gas cloud will collapse, and the last star will ignite. The universe will slowly transition from an age of light and fire into an age of darkness and decay, populated only by the fading embers of white dwarfs and the silent voids of black holes. Our universe is about 13.8 billion years old. Cosmically speaking, it's still in its vibrant youth. The red dwarfs that formed shortly after the Big Bang are barely into their lifespans, but the trend is unmistakable. Every new star that is born is one step closer to the very last star that ever will be. The life cycle of stars is the grand, rhythmic heartbeat of the cosmos. And like any heartbeat, it cannot beat forever. This journey through stellar evolution sets the stage for understanding the very distant future, a universe filled with the strange, haunting, and beautiful remnants of an age of light. Have you ever looked up at the night sky and wondered what will happen to all those stars? We see them as timeless, but they, like everything else, have a lifespan. And their story doesn't end in a blaze of glory. Instead, the universe's final chapter is a tale of slow, quiet fading, a cosmic twilight that will stretch on for trillions and trillions of years. Join me as we journey into the far, far future to meet the last cast of characters in the cosmic drama. Our story begins with the unsung heroes of the cosmos, red dwarfs. You might not see them easily, but they are everywhere. In fact, red dwarfs make up nearly 75% of all stars in the universe. They're the runts of the stellar litter, with less than half the mass of our sun, glowing with a faint, cool, reddish light. But what they lack in brilliance, they more than make up for in endurance. While massive stars live fast and die young, burning through their fuel in a spectacular frenzy, red dwarfs are the ultimate survivalists. They sip their hydrogen fuel incredibly slowly, like a connoisseur savoring a fine wine. Their secret weapon is something called convection. Imagine a pot of boiling water on a stove. The water at the bottom heats up, rises, cools, and sinks again. Red dwarfs do the same thing with their internal plasma, constantly stirring their fuel. This means they can use nearly all their hydrogen, not just what's in their core. Because of this incredible efficiency, their lifespans are staggering. We're talking trillions of years. That's far, far longer than the current age of our universe, which is a mere 13.8 billion years old. So, long after our sun has fizzled out, long after the brilliant blue giants have vanished, red dwarfs will still be shining. They will be the last flickering campfires in an ever-darkening cosmos, the final holdouts against the endless night. But even their fires cannot burn forever. Eventually, after an almost unimaginable stretch of time, their fuel will run out. And when it does, they will slowly cool and contract, transforming into the next players on our stage. White dwarfs. A white dwarf is the final glowing ember of a star that was once much like our own sun. When a star like ours runs out of hydrogen fuel in its core, it swells into a red giant, shedding its outer layers into space. What's left behind is the incredibly dense Cora white dwarf. Don't let the dwarf part fool you. A typical white dwarf has a mass comparable to our sun, but it's all been crushed down into a sphere roughly the size of the Earth. The density is mind-boggling. A single teaspoon of white dwarf material would weigh several tons on Earth. These objects don't shine because of nuclear fusion. Fusion is stopped. They glow simply because they are incredibly hot, radiating away the leftover heat from their former lives as active stars. Think of them as cosmic embers, slowly cooling over billions and trillions of years. They are the ghosts of stars, silent and solitary. Right now, the universe is filled with these glowing remnants. But as time marches on, they will continue to radiate their heat into the cold vacuum of space, fading from brilliant white to yellow, then to orange, finally to a dull red, until they emit no light at all. And what happens then? They become something purely theoretical, something the universe is still too young to have created, a black dwarf. We'll come back to them because their story has a surprising twist. Now let's talk about what happens when stars much bigger than our sun die. 4 stars, more than about 8 times the mass of the sun. The end isn't a quiet fade, but a cataclysmic explosion, a supernova. When these giants run out of fuel, Gravity wins the final battle. The core collapses in on itself with such incredible force that it triggers a blast that can briefly outshine an entire galaxy. What's left behind is one of the most extreme objects in the universe, a neutron star. Imagine taking up to 2 times the mass of our sun and crushing it into a sphere just 10 to 15 kilometers across about the size of a city. The density is beyond comprehension. A single teaspoon of neutron star matter would weigh 1 billion tons. The gravitational pull is so intense that protons and electrons are forced to merge, forming a sea of neutrons. That's where it gets its name. Neutron stars are cosmic laboratories for extreme physics. Their interiors might contain states of matter we can only dream of, like quark matter or strange matter, pushing the known laws of physics to their absolute limits. As the universe ages, these incredibly dense cinders will persist, spinning rapidly and emitting beams of radiation like cosmic lighthouses we call pulsars. They are the exotic, hyperdense fossils of the most powerful stars that ever lived. But there's another, even more extreme fate for the most massive stars of all. For the true titans of the cosmos, stars dozens of times more massive than our sun, gravity is an unstoppable force. When their core collapses, nothing can halt it. Not electron pressure, not neutron pressure. The collapse continues indefinitely, crushing matter into a point of infinite density, singularity. This creates a black hole, an object with a gravitational pull so powerful that nothing, not even light, can escape once it crosses a boundary known as the event horizon. For trillions upon trillions of years, black holes will be the kings of the dark universe. They will act as the final cosmic predators, sweeping up any stray matter, gas, or even other stellar remnants that wander too close. They will grow in size, becoming the gravitational anchors of dead galaxies. You might think they're eternal, the final winners. But even black holes have a lifespan, thanks to a bizarre quantum effect predicted by Stephen Hawking, now known as Hawking radiation. Black holes actually evaporate over mind-bogglingly long timescales. They slowly leak energy back into the universe, shrinking over eons. For a solar mass black hole, this process takes longer than any number you can comfortably write down. But eventually, after a span of time that makes the age of the universe look like the blink of an eye, even the largest black holes will radiate away into nothingness, leaving behind only a final puff of particles. This brings us back to the most common fate for stars, the black dwarf. Remember the white dwarfs? The cooling embers of sun-like stars? After quadrillions of years, that's thousands of trillions of years, they will finally cool down completely, reaching the background temperature of the universe. They will become black dwarfs, cold, dark, dead spheres of ultra-dense matter, completely invisible against the blackness of space. For now, black dwarfs are purely hypothetical. The universe, at just 13.8 billion years old, is far too young for a single one to have formed. But in the far, far future, the cosmos will be littered with them. Galaxies will be graveyards of these stellar fossils, a silent testament to a time when light and life existed. But even in this cold, dead future, there might be one last spectacular surprise. Theoretical models suggest that after eons upon eons, a rare quantum event called quantum tunneling could occur within the dense crystal structure of a black dwarf. This could trigger a sudden runaway fusion reaction of the carbon inside. The result? Black dwarf supernova? Imagine it. In a universe otherwise dark and silent, after an almost infinite amount of time has passed, a tiny flicker of light, a single solitary explosion, a final defiant firework in the eternal darkness. These would be the very last interesting events in the life of the universe. So let's lay out this timeline of cosmic twilight. In the next few billion years, stars like our sun will die and become white dwarfs. Over trillions of years, the last red dwarfs will finally burn out and fade away. After quadrillions of years, the first black dwarfs will appear, and the universe will become a dark realm of stellar remnants. And far, far beyond that, in a future so distant it defies imagination, the occasional black dwarf supernova might briefly light up the dark. The universe won't end with a bang, or even a whimper. It will end in a slow, graceful, and achingly long dimming of the lights. Each of these stellar objects, the enduring red dwarf, the cooling white dwarf, the extreme neutron star, and the all-consuming black hole represents another step in the fading of the cosmic fire, a final, quiet curtain call for the stars. We gaze up at the night sky, a canvas painted with the light of countless stars. We understand their birth, their brilliant lives, and their dramatic deaths. But what happens after the last star we know flickers out? What does the deep, dark future of our universe truly hold? We're about to journey to the edge of time itself to explore the mysteries of the very last stars. Astrophysics has given us a stunningly clear picture of stellar evolution. We know that massive stars explode in brilliant supernovae, while smaller stars like our Sun gently shed their outer layers, leaving behind a dense core. But when we look into the far, far future, trillions upon trillions of years from now, the certainties begin to fade, and the unknowns start to multiply. This isn't just science, it's cosmic speculation, a realm of exotic stars, strange remnants, and events that defy our current understanding. Let us start with a question that seems simple but is deceptively complex. How long can a star really burn? We often point to red dwarfs as the marathon runners of the cosmos. These tiny dim stars are incredibly efficient. While a star like our Sun will burn for about 10 billion years, the smallest red dwarfs could last for up to 10 trillion years. That's nearly 1,000 times the current age of the entire universe. They sip their hydrogen fuel so slowly, they seem almost eternal, but even they have a limit. Eventually, after an unimaginable span of time, the last red dwarf will exhaust its fuel. Its core will cool, its light will fade, and it will become a silent, cold object known as a black dwarf. And here lies the first great mystery of the cosmic twilight. By the time the final red dwarf fades away, will anything else in the universe still be generating light? Or will this be the moment the cosmos is plunged into its final, unending night? This is where things get truly weird. Our current models of physics predict some bizarre and wonderful possibilities. Could the universe host exotic types of stars we've never seen? Stars that don't play by the normal rules? One mind-bending idea is the quark star. We know about neutron stars, the incredibly dense remnants of massive star explosions. The pressure inside them is so intense that protons and electrons are crushed together to form neutrons. What if the pressure gets even more extreme? Some theories suggest that the neutrons themselves could break down, dissolving into a sea of their fundamental components. Quarks. Quark star would be even smaller and denser than a neutron star. Would it be stable? Could it exist for lengths of time that make even red dwarfs seem fleeting? We simply don't know. Then there are boson stars. These are purely hypothetical objects, but they're fascinating. Instead of being made of familiar particles like protons and neutrons, they would be composed of particles called bosons. Some physicists speculate that dark matter, the mysterious substance that makes up most of the matter in the universe, could be made of bosons. If so, could these particles clump together under gravity to form dark stars? These objects wouldn't shine with visible light because they wouldn't rely on nuclear fusion. They'd be powered by the physics of the dark sector, completely invisible to our telescopes, yet shaping the cosmos in unseen ways. The list of theoretical oddities goes on. There's even the concept of an electroweak star. This would be a star so incredibly dense and hot that deep within its core, the electromagnetic force and the weak nuclear force, two of the four fundamental forces of nature, would merge into a single electroweak force. Instead of fusion, these stars would generate energy through electroweak processes. If they exist, they would likely only form in the very early universe or under extreme far future conditions. But they represent another potential source of energy that could outlast every conventional star, pushing back the final darkness. Of course, we couldn't talk about the cosmic future without addressing the two biggest elephants in the room, dark matter and dark energy. Together, they make up 95% of the universe, and we barely understand them. Dark energy is the force driving the accelerating expansion of the cosmos. Will it continue to stretch the universe apart until it becomes a cold, empty void, the big freeze? Or could its properties change over time, leading to a completely different fate? And dark matter, with its gravitational influence, holds galaxies together. If dark matter particles can interact with each other in ways we haven't detected, they could form their own structures, their own dark stars, powered by annihilation or other dark sector physics. The universe could be teeming with hidden light and energy, a secret cosmic ecosystem operating just beyond our perception. The role these unseen forces will play in the long twilight of the cosmos is one of the biggest open questions in all of science. But perhaps the most spectacular prediction for the deep future involves not a new kind of star, but the ghost of an old one. Imagine a black dwarf, the cold, dead remnant of a star like our sun. It has floated in the darkness for quadrillions of years, a lump of carbon and oxygen the size of a planet. It seems inert, lifeless. But according to some theories, it has one last act. Over these immense timescales, the strange rules of quantum mechanics come into play. A process called quantum tunneling could allow the carbon nuclei inside the black dwarf to overcome their repulsion and fuse together. This wouldn't be a slow burn, it would be a runaway chain reaction. The result? A supernova. Not from a young, massive star, but from a stellar corpse that was thought to be dead forever. These black dwarf supernova would be the final fireworks of the universe. They would be incredibly rare, separated by eons of darkness. Imagine a single lonely flash of light illuminating the void for a few weeks before the eternal night returns. It's a hauntingly beautiful idea that even in a universe trending towards absolute cold and disorder, there can still be a spark of creation. This brings us to the concept of entropy. Stars are islands of order-low entropy systems, in a universe that naturally moves toward disorder, or high entropy. As stars burn out and die, the universe as a whole moves closer to a state of maximum entropy, often called heat death, where everything is uniform, cold, and unchanging. The great mystery is whether this march toward disorder is truly inevitable. Could exotic physics, like the kind that might form quark stars, or trigger black dwarf supernova, create new pockets of low entropy? Or is the death of the last star the true final milestone on the road to cosmic oblivion? But there's one more variable we haven't considered, one that could change everything: life, or more specifically, intelligence. We are a young civilization on a single planet, but what if life arises elsewhere? What if over billions of years, civilizations become so advanced they can manipulate matter and energy on a cosmic scale? Could a hyper-advanced civilization learn to feed dying stars, extending their lifespans indefinitely? Could they build artificial stars, perhaps by corralling matter around black holes to generate energy? Could they figure out how to harvest energy from the vacuum of space itself? If intelligence can survive and spread across the galaxy, the natural fate of the universe might be completely rewritten. The future of the stars might not be a purely mechanical process dictated by physics, but a story shaped by the choices of conscious beings. So as we look to the deep future, we're left with a universe of profound questions. How long will the very last red dwarf truly burn? Are there exotic, unseen stars hidden in the cosmic darkness? Will the universe end with a final lonely firework from a dead star? Can dark matter create its own secret sources of light? Is life destined to be a passive observer, watching the stars fade one by one? Or can it become the author of a new chapter? These mysteries transform the end of the universe from a simple astronomical forecast into a grand frontier of human imagination. They are questions that push the boundaries of our science and our philosophy, reminding us that even in the face of a seemingly empty future, the cosmos is filled with breathtaking possibilities. Have you ever looked up at the sun and felt its constant, reassuring warmth? It's been there for every sunrise, every sunset, every moment in human history. It feels permanent, eternal, but it's not. The universe's grand timeline, stretching across trillions of years, can feel abstract and distant. But for us, the fate of the stars isn't just some far-off cosmic drama. It's deeply personal. Our own star, the sun, is bound by the very same laws of physics that govern every other star in the cosmos. And its future will ultimately decide the fate of Earth, and with it, everything humanity has ever known. Let's start with the sun today. At about 4.6 billion years old, our star is comfortably middle-aged, about halfway through its main sequence lifespan. Deep in its core, it's a colossal nuclear furnace, relentlessly converting about 600 million tons of hydrogen into helium every single second. This process, nuclear fusion, generates a tremendous outward pressure. This pressure perfectly balances the crushing inward pull of the sun's own gravity, keeping it stable and shining steadily. But this delicate balance, the very thing that makes life on Earth possible, will not last forever. In about 5 billion years, the sun will run out of hydrogen fuel in its core. When that happens, its evolution will enter a new phase, one that is both spectacular and utterly catastrophic for our solar system. With the hydrogen gone, fusion will temporarily sputter out. Without the outward push from fusion, gravity will win the tug of war, and the sun's core will start to collapse and contract under its own immense weight. This contraction will dramatically increase the temperature and pressure in the core, so much so that a new fusion process will ignite. This time it will start fusing the helium that has been accumulating for billions of years. But something else happens simultaneously. While the core shrinks and heats up, the sun's outer layers will begin to expand. And I mean really expand. Our sun will swell into what's known as a red giant. Imagine a star so large that its surface extends all the way out to where Earth is orbiting right now. Mercury and Venus, the inner planets, will be engulfed without a doubt. They will be vaporized, becoming part of the sun itself. Earth's fate is a little more uncertain. Some models suggest it will be swallowed whole, while others predict it might just barely escape, left as a scorched, lifeless rock in a slightly wider orbit. But let's be clear, even if Earth avoids being directly consumed, it won't be a pleasant place. Long before the sun's physical expansion reaches us, the consequences will be dire. The sheer intensity of the bloated sun will boil away our oceans, strip our atmosphere into space, and turn the surface of our planet into a molten hellscape. Life as we know it will have ended long before the sun physically touches our world. This red giant phase will last for about 1 billion years. Afterwards, the sun will become unstable, will begin to pulsate violently, shedding its outer layers into space. These shed layers will form one of the most beautiful objects in the cosmos, a glowing, intricate structure called a planetary nebula. It's a vast, expanding shell of ionized gas, carrying the chemical elements that were forged inside the sun's core like carbon and oxygen out into the galaxy. This celestial artwork will be breathtaking but fleeting. It will shine for only about 10,000 years before it disperses and fades into the interstellar medium. And what will be left at the heart of this fading nebula is the remnant of our sun's core. Our sun is unmassive enough to explode as a supernova or collapse into a black hole or a neutron star. Instead, it will settle down into its final form, a white dwarf. This will be an incredibly dense, Earth-sized ball of mostly carbon and oxygen. It won't generate any new energy through fusion. It will simply glow with leftover heat like a cosmic ember. Slowly, over trillions and trillions of years of timescale, almost impossible for us to comprehend, this white dwarf will continue to cool and dim. Eventually it will radiate away its last bit of heat and become a black dwarf, a cold, dark, dead lump of matter floating silently in the infinite night. Our sun, the brilliant source of all light and life on Earth, will end its long journey as an unrecognizable, silent corpse. For Earth, the story ends much, much sooner. We don't even have to wait 5 billion years for the red giant phase. In just about 1 billion years from now, the sun's natural brightening part of its normal evolution will make Earth uninhabitable. The sun gets about 10% brighter every billion years, and that's enough to trigger a runaway greenhouse effect. Our oceans will evaporate, our atmosphere will be destroyed, and all complex life will vanish. By the time the sun actually swells into a red giant, Earth's surface will already be a barren, sterilized wasteland. The legacy of our planet won't be its physical survival. It will be in the atoms and elements that were once part of it. These materials, scattered into the cosmos by the sun's planetary nebula, might one day become part of new stars, new planets, and perhaps somewhere else, new life. Thinking about the death of the sun isn't just an abstract astronomical exercise. It's the definitive end of our home. It's a profound reminder that even the most constant presence in our lives, the daily rhythm of sunrise and sunset, is temporary on a cosmic scale. But this story also connects us to something much larger. Earth's fate isn't unique. Every planet orbiting a star is tied to that star's destiny. Across the galaxy, countless civilizations, if they exist, might one day face the same ultimate question. What do you do when your star begins to die? By tracing the sun's future, we see how the grand cosmic timeline touches us directly. Earth's story is just one small thread woven into the vast, beautiful tapestry of stellar life and death. And just as we look out into the universe to understand the fate of our sun, astronomers are constantly looking back at stars like ours, simulating, modeling, and piecing together the life cycles of stars across the galaxy. This scientific journey of discovery is how we've come to understand this incredible future, using our telescopes, theories, and computers to peer billions, and even trillions of years ahead. Have you ever looked up at the night sky and wondered about those twinkling lights? Every single one is a star, living out its own cosmic story. Some are young, hot, and blue, burning with incredible intensity. Others are ancient, red, and slowly fading away. But how do we figure all this out? How do we know where they came from, how long they'll live, and what their final fate will be? The story of this discovery is as epic as the stars themselves. It's a tale woven from centuries of patient observation, groundbreaking theories, and powerful computers that let us watch the universe age and fast forward. For most of human history, stars were seen as eternal, perfect fires in the heavens. Ancient civilizations viewed them as divine beacons, unchanging and permanent. The great philosopher Aristotle even proposed that the cosmos was made of a special fifth element, totally different from anything on Earth and incapable of decay. The naked eye, this made sense. Stars didn't seem to age or change apart from their slow, predictable dance across the night sky. The idea that a star could live for billions or even trillions of years was simply beyond comprehension. This eternal view of the heavens began to crack when the telescope arrived. In the 16th and 17th centuries, astronomers witnessed something impossible: new stars suddenly appearing in the sky, shining brilliantly for a few weeks or months and then fading away. We now know these were supernovae, the explosive deaths of massive stars. These dramatic events were the first real clues that the heavens were not as fixed and unchanging as everyone had believed. The universe, it turned out, was a much more dynamic and violent place. But the real breakthrough came when two scientific revolutions collided in the 19th and 20th centuries. Thermodynamics, the science of heat and energy, and atomic physics, the study of the building blocks of matter. At first, scientists like Helmholtz and Kelvin thought the sun was powered by its own gravity, slowly contracting and heating up. The problem was, this process could only keep the sun shining for about 20 million years. Geologists already knew Earth was much, much older than that, so something was missing. The answer finally arrived with the discovery of nuclear fusion. In the early 20th century, physicists realized that deep inside the sun's core, immense pressure and temperature were forcing hydrogen atoms to fuse together to create helium. This process releases a staggering amount of energy, and it was this energy that powers the stars. Suddenly, the puzzle pieces fit. By the mid-20th century, brilliant minds like Subrahmanyan Chandrasekhar and Hans Bethe laid out the complete framework for stellar evolution. Stars, they showed, were not eternal. They were born from vast clouds of gas and dust. They spend most of their lives in a stable phase fusing hydrogen. And then, depending on their mass, they die in spectacular and varied ways. To map out these newly discovered life cycles, astronomers developed a revolutionary tool, the Hertzsprung-Russell diagram, or HR diagram for short. This might sound complicated, but the idea is simple and elegant. By plotting a star's brightness against its color, which tells us its temperature, a hidden order emerged from the chaos of the night sky. Stars weren't just scattered randomly. They fell into distinct patterns and followed clear evolutionary paths on the diagram. There's the main sequence, a long, stable band where stars like our sun spend about 90% of their lives steadily burning hydrogen. Then, as their fuel starts to run low, they swell up into the red giant phase, becoming larger and cooler. And finally, they reach their ultimate fate. Smaller stars like our sun collapse into dense glowing embers called white dwarfs.
Wow.
More massive stars end their lives in a supernova explosion, leaving behind either an ultra-dense neutron star or, for the most massive of all, a black hole. The HR diagram became a cosmic roadmap, allowing us to look at any star and understand where it is in its life story. Just when we thought we had it figured out, another revolution came along: the computer. The late 20th century supercomputers became powerful enough to turn these theories into dynamic, living models. Astronomers could now simulate not just one star, but billions of them evolving together inside entire galaxies. Projects like Illustris, EAGLE, and Tiang 50 are digital universes in a box. They model the birth of stars from swirling gas clouds, their lives, their explosive deaths, and how the heavy elements forged inside them are blasted back into space to form new stars and planets. These simulations are like a time machine. You can watch a galaxy form, see it light up with a flurry of star birth in its youth, and then witness how star formation gradually slows down as the galaxy ages. We can see how the Milky Way will interact with its neighbor, Andromeda, in about 4.5 billion years, triggering a final, spectacular burst of star formation. We can watch what happens after that, as the lights slowly begin to go out. One by one, until only the faint, long-lived red dwarf stars remain, casting a dim red glow in a quiet, fading cosmos. To ground these incredible simulations in reality, astronomers turn to some of the oldest objects in the universe, globular clusters. These are ancient, tightly packed, spherical collections of hundreds of thousands of stars, all born at the same time. They act like cosmic clocks. By looking at which stars in a globular cluster are starting to die, astronomers can precisely measure the cluster's age. Because these clusters are so old, they give us a minimum age for the universe itself. These cosmic clocks, combined with other measurements, have helped us determine that our universe is about 13.8 billion years old. The journey to understand the life of stars really mirrors humanity's own evolving perspective. We started by seeing the stars as perfect, eternal, divine lights. Now, we understand them as physical objects, born from dust, powered by nuclear fire, and destined to die. They are subject to the same laws of physics that govern our world and our very bodies. The stars in our sky are not immortal guardians, but beautiful, fleeting episodes in a cosmic drama that will play out over trillions of years. And through our simulations, we've gained an even more profound, almost humbling perspective. By compressing cosmic timescales into mere minutes of computation, we can watch not just stars, but entire galaxies fade away. We can peer into the deep, distant future, long after the last star has flickered out, and foresee a universe slipping into a final, cold, and silent age. This ability to look forward, to reconstruct what must eventually come, is one of the most remarkable achievements of the human mind. It is our gaze, stretching not just across space, but across time itself. Have you ever looked up at the night sky and felt a sense of timelessness? The story of those stars is also the story of time itself. From the blazing birth of the very first suns to the quiet flicker of the last, starlight is what makes our universe visible, structured, and alive. But what happens when that light goes out? What comes after the last star fades? Let's journey to the very end of time. Right now, the universe is still bright, but it's already dimming. Star formation peaked about 10 billion years ago and has been slowly declining ever since. Think about it. Our own Milky Way is already producing fewer new stars than it did in its youth. Fast forward 100 billion years, and most galaxies will have burned through all their cosmic gas reserves. Star birth will come to a halt. Imagine a universe 1 trillion years from now. The only lights left will be the faint, stubborn glows of red dwarfs. These tiny stars are incredibly efficient, sipping their fuel so slowly that some can last for up to 10 trillion years. But even they have an expiration date. Beyond 100 trillion years, the last red dwarf will finally fade to black. The era of starlight will be over. At this point, the cosmos enters what physicists call the degenerate era. It's a universe ruled not by burning suns, but by their ghosts, the stellar remnants. We're talking about white dwarfs, neutron stars, and black holes, all drifting silently through an eternal night. Let's look at the fate of these remnants. White dwarfs, the dead cores of stars like our sun, will spend trillions of years cooling down. Eventually, they'll crystallize and become what we call black dwarfs, cold, dark spheres of carbon and oxygen, completely invisible against the blackness of space.
Ow.
But they might not be entirely quiet. Some theories suggest something incredible could happen. After an almost unimaginable amount of time, a number with more zeros than there are particles in the known universe quantum, Tunneling could trigger a sudden supernova explosion in these dead stars. These black dwarf supernovae would be the very last fireworks in a dark universe rare. Scattered flashes of light interrupting an otherwise eternal silence. It's a mind-bending thought. A final, unexpected burst of brilliance at the end of everything. Neutron stars and black holes will stick around for even longer. But even they aren't eternal. Thanks to Stephen Hawking, we know that black holes aren't truly black. They slowly evaporate through a process called Hawking radiation. The largest, most massive black holes at the centers of galaxies could take up to 10 to the power of 100 years to disappear. A Google years. As they vanish, they'll radiate their energy away until only the faintest whispers of heat remain. The last sigh of a once mighty giant. Wow, as the last black hole evaporates, the final trickle of photons, the last particles of light, will spread out into the infinite darkness. The universe, which began in a flash of blinding light, will be reduced to a temperature of near absolute zero. A cold, thin, uniform fog of fading energy, stretching out forever. At that point, time itself becomes almost meaningless. With no new sources of energy, no stars, no galaxies, and no light, the universe becomes a place of absolute stillness. A cosmic graveyard of scattered matter and energy, spread thinly across an infinite black expanse. It's the ultimate silence, the ultimate end. This raises one of the most haunting questions of all. Could life, in any form, endure in such a cosmos? Based on what we know from physics, the outlook is bleak. Life as we know it is a process that depends on free energy indifferences in temperature and pressure, on flows and gradients. Stars provide that energy now. But when they fade, and the universe becomes thermodynamically uniform, there's no energy left to power complex processes like biology or even thought. Of course, that hasn't stopped scientists and philosophers from speculating. Some have proposed that hyper-advanced civilizations might find ways to survive, perhaps by harvesting energy from the spin of black holes or tapping into exotic quantum processes. Others imagine that life could enter a state of extreme hibernation, waking up only for brief moments over trillions of years to stretch its existence across the eons. But these are really just fascinating thought experiments, not realistic survival plans. They're more a testament to our own hope and imagination than a likely scenario for the far, far future. So what does this all mean for us, right here, right now? The most important takeaway isn't whether some abstract form of life can survive in the distant dark. We are unbelievably lucky. We live in a privileged moment in cosmic history, the Stelliferous era, the age of stars. An era when the universe is filled with light, galaxies are blazing, stars are shining, and planets like ours can orbit in warm, habitable zones. The cosmos is alive with activity and bursting with possibility. Humanity will almost certainly never witness this far future. No civilization, no matter how advanced, can last for trillions of years. But by imagining it, by studying the physics that describes this distant future, we connect ourselves to the full, magnificent sweep of cosmic history. We become active participants in a story that stretches from the birth of the very first stars to the profound silence of the last. When that final star burns out, the universe won't end with a bang, but with a quiet, fading whisper. Darkness will reclaim the sky, and the brilliant age of starlight will become just a memory, written only in the ghostly structures left behind. Yet we are here now, this perfect moment, able to look up at the sky, to study this future, and to wrap our minds around the fate of stars billions and trillions of years from today. That knowledge in itself is extraordinary. This means that even in a universe that will one day go dark, the light of human understanding, of curiosity, is burning brightly within us. The stars will fade, their light will vanish, but the story they told us, a story we have only just begun to understand, that will not. Thank you so much for joining me on this journey to the end of time. If you found this as fascinating as I do, please hit that like button and consider subscribing for more deep dives into the cosmos. See you in the next one.